Hello, this is Mr. Collier, and today we're doing some exponential applications. So in this first example, the length L centimeters of a pumpkin plant increases according to the equation. Let me write this a bit clearer. L equals 4 times 1.2 to the power of t. Okay, where t is the time in days. So we're going to fill this out now. We're going to fill out the size of the length of the pumpkin plant at 0 days all the way up to 16 days. And one way to do that actually is probably pretty easy to do that with the graphing calculator. We can type in the function here, 4 times 1.2 to the power of x. And then if we graph that, I'm going to go to zoom 6, zoom standard. Let's see if that, actually we don't need the graph, we need the table right here. So I'm going to go to second function table. And right now I've got my table set up to go up by 5, so I'm going to just go to second function table set. And my table is going to start at 0, and it's going to go up by, I guess I can go up by 2's. And then if I go back to second function table, then I get the values at 0, 2, 4, which is what I need, right? So actually let me copy this and paste it over here so I can see it. Alright, so at 0, the initial length of the plant is 4, and then it's going to be 5. I'm going to use two significant figures here because I don't have much room, so it's 5.8. After 4 days it's 8.3. After 6 days it's 11.9. 8 days 17.2. 10 days 24. Oh, well, there's just one decimal place just to keep it nice and accurate there. 12. 35.7. And I need a couple more values here on the calculator, so I'll just scroll down here. Alright, so let me get those. Okay, so I get 14 days, 51.4, 16 days, 73 point, well actually I round that up to 74.0. Okay, so draw the graph of t against c for this interval of t and this interval of L. So actually I'm going to do that on the graphing calculator as well. I've already got the function in there, but this indicates the domain range, so I'm going to change the window to go from 0 to 20, the x values, and 0 to 100 with the y values. I'll graph that now. And that's what the graph looks like there. Okay, we can see the y-intercept is 4. So actually, they just want to. Oh, they do want you to draw it. So that's gonna take a bit of time here. Okay, so now we're going to graph these coordinates. I'm going to set up some axes. We don't have any negative values or anything like that, so I'm going to set it up like this. Maybe like that. And perhaps use red. My x values, or in this case t, are going to go up to 16. So I'll probably go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's good. It goes up to 16 there. You can label your axis down here. This is time. Time in days. Okay, and over here we're going to have length in centimeters. And we want to go up to actually about 74. So maybe go by tens. 10, 20, 30, 40, 50, 60, 70, sure. Okay, we'll go up in tens. That's 10 right there, 20, 30. Alright, so you can fill in some values there. Okay, now I'm going to plot these points. Y-intercept's 4, so that's down even below 10. That's going to be around right there. 2, 5.8 is still going to be less than 10. Still less than 10. It's a little bit more than 10. Oh, whoops. Made a mistake there. The X values are going up by 2, so just let me undo. Okay. So watch out for that. There's the y-intercept. Now I go over 2, 5.8, halfway up 10, and 8.3. Oh, sorry, 8.3. Then I go over 2 more, and 11.9. Go over 2 more, 17.2. So we're not quite at 20. Go over 2 more, and we're up to 24.8. So we're seeing some increasing here. And go over 2 more, we're up at 35.7. Over 2 more, we're up to 51.4. And over 2 more, we're up to 74. So there's your graph. We can draw the curve now. There we go. How long is the pumpkin when t equals 0? That's going to be 4 centimeters. Okay, like in our table on our graph. How long will the pumpkin be after 3 weeks? So 3 weeks is 21 days. So we can actually use a formula, and the length equals 4 times 1.2 to the power of 21. So let's use our calculator to figure that out. Okay, so 4 times 1.2 to the power of 21 equals 184. So that's 184 centimeters. Okay, let's look at another example here. Hubert invests 3,000 euros in the bank at 5% per annum, compounded yearly. Let Y be the amount he has in the bank after X years. Draw a graph to represent how much Hubert has in the bank after X years. Use a scale 0 to 10 years on the X-axis. So for part A, we're going to write an equation first. So he starts off with 3,000, that's the initial value, and we're increasing at a rate of 5% per year, so you could do 1.05 to the power of X in order to get the amount of money he has in the bank at any given year. Okay, so we've typed that in our calculator. So we'll type that in, we'll get 3,000 times 1.05 to the power of X. Can I leave that? Okay, good. The window, we want 0 to 10 years. So that's 0 to 10 years. And the Y values, they said they wanted 2,500 to 5,000. 2,500 to 5,000. 1, 2, there you go. So now I'll graph that, and it looks very straight, but actually it is exponential. Okay, you'll see later on. Well, it's only 5% per year, so it's pretty close to being straight, but it is exponential. So that's our graph. We're going to graph that on some axes here. Okay, so we're going to graph this now. We're going to maybe I'll set up some axes here. Now we want to start off at 2,500. So I won't write in the x-axis here because we're not going to see that. I'm going to start off at 2,500. We're going to go up to 5,000, so maybe go up by 200, so that's 2,700, 2,900, 3,100, 3,200, 3,500 here. Oh no. That's 27, 29, 31, so I'm going to go by 2, so that's 3,900. 4,100, 4,300, 4,500, 4,700, and this is going to be like 5,100 here. And this over here is the we have the bank balance. Okay, bank balance in euros. How many? Okay, so what? And the x-axis here, we're gonna go 0 to 10 years. All right. So actually, I'm gonna make a little symbol here to show that we've have a break in the graph. We have a break in the y scale. Okay, so I'm going to just do that. And I'll make my x-axis now. X-axis, okay. So on the x-axis we have 0 to 10 years, I believe. Was that correct? 0 to 10 years. So I got a lot of space. I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's time in years. Alright, so I'm going to start plotting some points here. Draw a graph to represent. Actually, let's get that table from our calculator. And I'm going to go to table. Now, right now I'm skipping 2. I want to go to table set. My starting value is 0 years. I want to go up by 1s. So I'll go over to the table now. Oops, second function graph gives me the table. And here I have the values up to 6. So I'm going to copy that, paste it over here. Okay. So time to plot some points. We have 0, 3,000. It's right there. 1, 3,150. 2, 3,300 is about there, right? 3, 37, 72. 4, 36, 46. So it's going to be about there. And next we're going to have 38, 28. And 4,020. About there. Go back to my calculator. I'll get the rest of those values down here. 7, 8, 9, 10. Okay. Alright. So 7 is 4221. It's about there. 8 is 4432. Then we have 46, almost up to 47, and 48, almost up to 49. There we go. Okay, we can draw a curve through this almost straight line. It's so close, but eventually it'll start getting look more and more exponential. Alright, so that is our graph. How much does he have after 4 years? Well, we can use our equation to find that exact answer. How much is after 4 years? That's going to be x equals 4. 1.05 to the power of 4. And actually, we can go to the table and check out 4 is 3,646 euro and 50 cents. So 3646.50, 3646.50 euro. All right, see how many years before Hubert has 4,000 euro in the bank. So you could put in 4,000 in the equation and solve it using logs, or we can check out our table and see when it's going to be 4,000. So actually at year 6 we're going to have 4,000. So after 6 years, Hubert has 4,000 euros.